All right, yesterday, yes, I know we already did this, but I do need to start from somewhere that kind of makes sense. So yesterday we started with weathering. So we do know that weathering is the breakdown of rock, making it smaller. There's two types, physical and chemical weathering. And we got into talking about physical weathering only yesterday, I believe. Why is this not going away? We don't need a reference table for this chapter for the most part. So anyway, physical weathering, nothing changed with the rock except for its size. It does happen in cold, moist climates more than warm, moist climates. And the rocks are exactly the same, just smaller. And remember, when the rocks break, they make more surface area, so more surface is exposed to the air. We started talking about some of the types of physical weathering. I believe we only got to the first two. So we talked about frost wedging and root pry. Anybody want to kind of refresh our memories with frost wedging? Sarah, what's the general gist of it?
Freezes and melts.
Freezes and melts. And what happens to water when it freezes? It expands. So yes, it does turn to ice, but it expands. So when water gets into the cracks in the driveway or the road, it freezes. Then when it freezes, it expands, makes the crack bigger. When that happens over and over and over again, we end up with some nasty looking potholes. Then the other one that we ended with yesterday is root pry or root action. This is when those baby roots grow in or under rocks or driveways or sidewalks or foundations. And when those baby roots get in there and then they grow into big, massive roots, that constant growing pressure will basically crack the rocks. All right, then we're going to move on to the next one, which Sarah actually brought up this one when I asked kind of some examples of how rocks could get worn down. She said when they bump into each other, and that has a fancy name. It's called abrasion. So this is the third box on page 1 still. So abrasion is just a fancy word for when the rock, I call it the bumping and rubbing of rocks when they collide. So when these rocks collide, they will become smaller, smoother, and rounder. So this is the first one I don't think you have in your notes. So go ahead and add this to the third box. So I just grabbed 2 different rock samples out of the closet there. What do you notice? What's the big difference you notice about these 2?
One's round and one's sharp.
Okay, so not that side. One's rounder and smoother, one is sharper. How do you think this round one got nice and sharp? Or not nice and sharp, the opposite of nice and sharp. How do you think this round one got so smooth?
Abrasion.
Through abrasion. Great job. So how do rocks move? How can they bump and rub against the other rocks?
Water.
Running water is the main time this can happen. Wind can cause it too. We'll talk about that. How do rocks move in water? So current. One example is a current. Now a rock like this. Is it picking up this rock? Most, like, is it picking it up and going down the river like this? Not unless it's a really strong river would it be able to pick up. No one is talking to you, that's why. Sorry, talking knowledge. Rivers don't go fast enough to pick up this rock. So how will this rock, if you were to watch it move in the river, what would it be doing probably? It could be sliding on the bottom, or another thing it could do is roll. And when it rolls, it's going to be bumping into other rocks or the bottom of the stream, whatever it's bumping into. Same with this guy, the one that's not rounded yet. What's gonna happen to this one as rubbing and bumping into all the other ones? It's gonna break, all the little sharp edges are gonna break off of it, and it's eventually going to become a much smoother, but yet smaller rock. The rocks that move around in rivers tend to be smaller, smoother, and rounder because of abrasion. That's abrasion. The third and final one is exfoliation. I'm sorry, the fourth and final one is exfoliation. You heard the word exfoliation before? In real life? Yeah, when you
Exfoliate your skin.
you exfoliate your skin. So you can either exfoliate your face, or if you're getting a pedicure, they do your feet. What happens with exfoliation? Like in that terms, what are you doing to your skin?
Taking the dry skin off.
Taking the dead, dry layers of skin off. And that's similar because we're not, oh, shoot, I forgot to talk about this. Going back to abrasion. So this is actually a beach that I used to go to in Massachusetts when I was, last time I was there was around your age. What do you notice about this beach? Okay, so first of all, do you see how many rocks there are? The whole beach itself, the entire beach was covered in rocks. And then you guys already said this, they're all smooth. How did all of the rocks get smooth?
The waves brought it
The
on.
waves, every time a wave came in from the ocean, it would push the rocks and they would roll up the beach. And then when the waves would go out, the rocks would roll down the beach. That constant rolling all day, practically all day long, every day, made the entire beach covered with these small, smooth, round rocks. Just to give you an idea of how big and how many rocks there were, I know this isn't a great picture, but you can see, like there's people, this whole beach is covered with round, smooth rocks. But it does hurt, but not like if you stepped on a bunch of jagged rocks. So it's still not like comfortable. I don't want to walk on hard rocks, but it's not like they're gonna poke at you.
Is that you in the ocean?
No, it's not. I found this on the internet because I hadn't been there since I was your age. So funny story. Went back my uncle had lived there his entire life. He was 90 when he died. This beach was always looked at like that his entire life. I went back this summer for the first time in like 20 years. Not a single rock left. So we found some locals, and they said one of the hurricanes that came through washed every single rock away. Not one single rock left. It is crazy. We were blown away. I wanted to bring back some for my classroom. Not one rock. You couldn't even find one rock in this whole beach. It was weird. It's very, very weird. Okay, now exfoliation. Just like when you exfoliate your skin, you take off the top layer or the couple top layers of skin. Exfoliation here is when the surface of the rock peels off. So you're basically peeling off layers of the rock.
Bless you. Yes. Appreciate it.
It's in tight.
What?
Salud.
Oh, is that what it was?
It technically means health.
Oh,
In Japanese.
German. I have a picture of this. This is like an extreme case. So you can see here, this hill had huge layers of rocks on it, and the top layers are just peeling away. So just like when you exfoliate your skin, you're peeling away the top layers. So that's physical weathering. Can you give me the main idea? What happens to rocks when they physically weather? How do they change?
Small.
They get smaller. That is the only thing that changes. So their size and their shape will change with physical weathering. Chemical weathering is different. They still break down, but with chemical weathering, so we're on the top of page 2. Now we're going to change their chemical composition. They're going to go through a chemical reaction like chemistry. This happens in warm, moist climates the most. It doesn't mean it doesn't happen here, but it happens more in warm, moist climates. And the kicker is This only happens on the surface of rock, not the inside. They have to be exposed to the air. Have you guys ever done any chemistry made of chemical reaction in your life? What chemical reaction have you done? Yeah, that's where I was getting at, baking soda and vinegar. With baking soda and vinegar, a chemical reaction happens, and in the end, there's a brand new product. You don't have baking soda and vinegar anymore. You have this mixture of the two that where the bonds break and rebond with new things. And the same thing happens with chemical weathering. You take two things and you change them completely into something new. I know. It's actually tied.
Just not well.
Yeah, see, there's a knot.
I'm thinking for triple M, so.
You actually can't. It's not on the-
My brother tripped over his shoelace and broke his arm.
Did they at least get it on video?
No, this was wild.
Oh, that was a disappointment. What? No.
I'm gonna start tying my shoes like that.
All right. So like I said, you guys kind of know the gist of a chemical reaction with the whole baking soda vinegar stuff. We're going to give a perfect example of chemical weathering, and the best one I can think of is rust. What do you guys know about rust?
It gives you,
It gives you headache?
tetanus.
Oh, tetanus, it does, okay.
That's
What did you say about rust?
Happens all the time.
Oh, it does happen all the time, it does.
Like it's on like cars and.
Cars.
bikes,
Bite,
Iron.
holes,
Anything metal.
that's what I was getting at, anything metal. Does anybody actually know how come, my new car isn't rusty?
No.
Hasn't had enough contact with water. Where does the rust happen on cars? Okay, bottoms, outside, why are old cars not completely rusty?
Because not all of it gets wet.
But why?
I don't know.
What about cars makes them not rusty all the time? They have paint on them. What does the paint do to the metal? Protects it. What is it not exposed to? Water and air. The paint on a car makes it so the metal does not get exposed to the water and air. Rust will happen once that paint gets removed. So if you scratch your car, there's going to be paint, rust there. Bikes, same idea. Tools, because tools don't have much paint on them. You leave them out. You could listen to my father-in-law yell at people, but that's where the rust is going to happen, is when the tool gets left outside. So rust happens when metal is exposed to air and water. Now, rust, there's let me go back a step. Rust has a fancy name, because why not? Everything has to have a fancy name in earth science, right? And that fancy name is oxidation. I don't think I did this. Where the word says oxidation, can you add in big letters rust? So you don't forget that.
Roost.
And right here it says iron. Actually, no, I'm gonna do this on here. No, I'm not, because it's recording on Zoom. Where it says iron, just change that to metal. So rust happens specifically on iron, but there's other types of oxidation that happen on other metals, and it's technically not called rust, but it is called oxidation. But anyway, that's too much information. Basically, rust happens when metal combines with oxygen. Just like the vinegar and the baking soda combine to make something new, metal and oxygen combine to make rust. Now, is the rust the same as the metal it used to be? What's different about rust than what it used to be? It's a different color. What's another difference? Different texture, instead of being nice and smooth, it's all bumpy. What else do you know? Okay, it's sharp sometimes. How strong is it compared to the metal it used to be? Right, it's pretty weak. You can poke your finger right through a rusty spot because rust is weak. So its properties have completely changed. So that's because rust is something completely different than what it used to be. Now you know pipes and bikes and cars can rust. So I have just a picture. Oh wait, actually I don't. What is this a picture of? Did you say it? It's a rock with rust on it. How can a rock rust?
It's all wet.
Because it has some sort of iron in it. So I could get this rock wet here and it would never rust. But if I get rocks that contain iron, they can rust. What happens when water goes through rusty pipes?
It becomes brown.
It gets that rusty color. It's really not bad. It's not desirable, but it's not a horrible thing. Well, if we put water over rusty rocks, what do you get? Rusty water. So the same thing can happen. When I break those rusty rocks, what do they turn into?
Red.
Well, they're already red, but what? Rusty sediments. So just broken pieces of rock. So then you could get rusty dirt. If there's rocks that have rust on them and then they break up into the dirt. I know, I wanted to go back here. Do you guys remember how I have a llama? I never told you guys I have llamas. Didn't I show you pictures at the beginning of the school year? No, I switched it up and showed you all the pictures of my dogs. That's because my favorite llama actually died, so I don't talk about him as much. But back when I was your age, we used to go on llama shows all over the country. And we went to a llama show in Georgia. And all these llamas were pink.
What?
Like a pinkish orangish color.
What, they spray paint them out?
So we're like, how do you get pink llamas? Like, what kind of llama is this color? It was like an apricot color. So not quite pink, not quite orange, but apricot. They were beautiful. We're like, and all of these llamas from Georgia were apricot colored. Turns out they were white llamas that rolled around in rusty dirt. And they were basically stained red. So we could never have a pink llama here in New York because we don't have rusty dirt like this. So if we brought those pink llamas from Georgia here, their pink would wear off if they didn't roll around in the dirt. Yeah, it's like an orange, it's like this color, it's like an orangish reddish color. If you are a Walking Dead fan, the first few seasons of Walking Dead when they were still in Georgia, if you notice the scenery or the color of their dirty clothes, it was a reddish dirt. It was not like a dirt like we're used to seeing. It was like a brownish reddish dirt. What? The llama was that color. They were a little lighter because they didn't get stained like they didn't like live in it. They just rolled around and then it like wore off a little bit, but it stained their white fur pink.
You actually have one?
I only have one now because Diablo died. I'm only left with Chester now.
Is he lonely?
No, he lives on a llama farm with other llamas.
Oh.
So yes, and then here's the classic example of rust that you're all familiar with. But what about the Statue of Liberty? She's not rusty.
It's not metal.
She is too. What is she made out of? What is it? Copper, somebody said it.
They cleaner.
Hey, she's made out of copper. What else is made out of copper? Pennies. So why isn't she the color of a penny if she's made out of copper?
Because you can't.
She got a protective layer.
She is not painted.
They spray painted.
They did not.
Why?
She rusted. She technically oxidized. It's not called rust on copper. It's called a patina. And so she's both.
At one point, it was a different color.
Yes, at one point when they were first building her, she was the color of a penny. Where is she standing right now?
New York City.
New York City, surrounded by
Water.
water. She's on an island. So she's surrounded by what kind of water?
Fresh water.
Salt water. She's surrounded by ocean, which is salt water. What happens is when copper reacts with salt water, it turns this greenish bluish color. Have you ever seen a greenish bluish penny?
Yeah,
Do you know where you find them a lot?
on the ground.
On the ground. Mhm. Okay, yes, in the mountain. Typically around here, you could probably go out right now and find some green pennies outside. Or at the end of spring, you can find some green pennies. The salt from the parking lot, the salt from the road reacts with the water, the melted snow, and it'll change pennies to this greenish brown or greenish, bluish color. Yeah. Because there's still a lot of salt water in the air there. So even though she's not submerged, that salt water kind of gets in the air. Like it evaporates a little bit and gets in the air. But, fun story. You guys remember where she was built? I know you learned this. She was built in France.
Come on.
Back, I don't know exactly when, because I'm more of an expert on the science, not the history part of her. So back when she was built, it was during the Industrial Revolution. And she turned a different color. Instead of that copper penny color, she turned a color like this penny here. Well, there's not much to see. What color is it?
Black.
Black. When they were building the Statue of Liberty, her copper color changed to this color. Why wasn't it green like it is in New York City? So she's not surrounded by water. She was surrounded by the air of France in the early whatever it was, but during the Industrial Revolution. What was there a lot of in the Industrial Revolution? Pollution. That was the start of the pollution. Because lots of factories, lots of pollution. They were burning coal. Coal releases a sulfur smell. Sulfur pollution. What does sulfur smell like? Remember?
Eggs.
Eggs. It's that stinky pollution smell. If you surround a penny by sulfur, it will turn this black color. So the pollution, not just, she didn't just get covered in soot or anything. Her metal reacted and changed to this black color. Now, why do I have a black penny? Because these are from the mineral lab. Remember doing the mineral lab?
Yeah.
Well, I used to keep every mineral in these boxes. Like, this is not how you guys saw them, but basically this box had a piece of sulfur in it, and I made the whole box filled with sulfur, and it changed the penny black. Just like the Statue of Liberty.
How long did it take?
It was from the first year I did it to the next year it had turned black. So I don't know in between if it took 6 months. Do it. You can do it. The reason I know all of this is because I did this in college, is I turned pennies all different colors.
Where do you find sulfur?
I'll give you a piece.
Okay.
So you can do it with sulfur, you can do it with ammonia. It'll turn a purplish color, I believe, with ammonia. You can turn it to a bright blue if you can expose it to just nitrogen, which you cannot, but you can in a chemistry lab. It changes, you can make all different colors with copper.
What if you turn it next to the heat?
Um, Like fire?
Yeah.
I don't know, actually, that was not part of it. I don't remember.
I think it just looks.
It might
Like,
just get a
might
soot
get
on
like-
it then. But anyway, let's keep going. Let's finish this up. The next one is carbonation, which is actually just acid rain. And if I don't already have acid rain on your paper, please add acid rain next to the word carbonation. Acid rain, by the way, is actually natural. It's not just a type of pollution. Acid rain happens anytime, well, water, let me rephrase this. Water becomes acidic anytime water and carbon dioxide are together. So the air you exhale, when that combines with water, can make some acid. So natural rain is slightly acidic anyway, but then when we started polluting the world a little bit more, there was more carbon dioxide, so more acid rain. If you remember when we learned about minerals, remember the back page of the reference table? Was there something fancy about acid in some of the minerals? Some of them bubbled with acid, just like the bubbling with hydrogen, or not hydrogen peroxide, what we were just talking about, baking soda and vinegar, it bubbled just like that. It was a chemical reaction. That acid was actually eating away at those minerals. So if we make things out of those minerals, remember marble is made out of calcite. So if we made a statue or a gravestone or a building out of marble, and then acid rain lands on them, they'll bubble and wear away just like the mineral we had in class did. And here's an example of that. Now, this is a very extreme case, but I'm sure you've seen old gravestones if you've ever gone in a cemetery where you can't read them at all. That's because they were made out of marble. And the marble reacted with the acid in the water, and eventually, after many years, it just completely wore away. We don't make gravestones out of marble typically anymore. Now we use granite, like this one that's up here, because granite doesn't have calcite in it. Here's another picture. This would be of a statue. You can probably didn't look like that originally, but here's a better one. Right there. Check out this statue. The first picture, it says it was taken in 1908. The second picture was taken in 1968. Notice any differences?
She doesn't have a face.
Yeah, so her face completely, like, almost looks like it melted away. It got eaten away. Same with her fingers. You can see the fingers in the first statue. I think her whole hand is gone by the second picture. What was so, by the way, she wasn't new in 1908 either. What do you think happened between, what do you know happened between 1908 and 1968?
50 years ago.
Well, yes, you did that math fast.
You just said 60.
I know,
Oh.
anyway, what have you guys learned in history happened in between that time?
War.
Again, no, well, yes, there were wars,
Pollution.
a lot of pollution. Again, the Industrial Revolution before 1908, we didn't have lots of polluting factories that would put out a lot more carbon dioxide that would then combine with the rain to make acid rain. I just searched for this. I don't know the name of this statue, so I looked to see what she looked like now, and I couldn't find anything. I would assume they may have started putting like a protective coating on them. I'm not sure.
She just disintegrated.
She completely disintegrated, and that's why I can't find her. But I found this picture lots and lots and lots of times. And the last one is hydration. And you guys know what it means to hydrate something?
Yeah, you gotta always hydrate.
Okay, you gotta always add water. So grab your Stanley cups and add water to rocks, and you're gonna weaken them. Really what's happening is that the water will disintegrate or get rid of that like cement that was keeping the sedimentary rocks glued together. And now we're going to make them super weak, and they're gonna end up crumbling.
That's what happened to that one statue.
That is not what happened to that statue. She was eaten away by acid rain combining with her marble.
No, I just punched it so hard.
That's it. You're super tough like that. That was also sarcasm, if you need me to tell you.
Oh,
Damn, wait, I wanna take that.
One
I want you to.
One last thing for today. Woohoo! And we're gonna talk about resisting arrest. Okay. You guys know what that means if someone was resisting arrest?
They're under arrest, but they're not willing to go.
They're not willing to go. That's a really good way. They're not just sitting there and saying, okay, arrest me. They're fighting. They're not letting the arrest happen easily. Okay, anyway. So if someone, okay, you're right. So it'll get, I don't recommend it, but anyway, if you're resisting arrest, you're preventing the arrest from happening. So you guys know what the words resistant means then. So let's talk about being resistant to weathering. If something was more resistant to weathering, what's that mean?
It's less affected by it.
It's less affected by it. It's not letting the weathering happen. What if it's less resistant to weathering?
What?
It's just gonna let it happen. Just let the weathering happen. Because there, again, remember how I said the Regents can't just use nice, easy to understand words? They will not say it's easy to weather or it's hard to weather, they will say it's either less resistant or more resistant to weathering. So in the composition section there at the bottom, I want you to add weaker, less resistant rocks weather away faster. So add that and then we'll talk about the picture. You don't have to write, well, actually, yes, you should write this one. In the diagram, shale, layer A is less resistant than the other rock. But will it help if I tell you this is the last we're writing today?
Liar, we have homework.
Well, okay, that's only circling.
No, we have stuff.
No, you don't. I'm gonna tell you, you don't have to do that top chart.
Oh, thank
No
you.
problem.
So you said circle answers.
Well, I think you should probably read them. as well.
So like if I don't have it done tonight. But you should. I will.
Mm. So again, we'll talk about this once we get it written.
Did you do the homework?
I know it's about this. I've never asked for these questions homework ever. I claim up. No, you don't.
So here we have a diagram. Each one of these different symbols is representing a different rock type. Do you guys remember these symbols when we talked about rocks? You don't have to officially remember now, but I'll just point out so you don't, well, you probably already think I'm crazy, but not for this.
Yeah, we do.
I know. So remember when we talked about the igneous or the sedimentary and metamorphic rocks, the very last column? So that's how I knew, you don't need to know this off the top of your head, but that's how I knew A was shale, because the dashed lines match up with shale, the blocks match up with limestone, the sideways or the pushed over blocks, they're dolostone, and this one's siltstone. Again, not important till next chapter, but just so you know where they came from. So why were they saying that A is less resistant to weathering? What happened to A? It got affected the most. It's been worn away the most. So which one is most resistant to weathering? D, because it's held up the longest according to this picture. So as Carter pointed out, our homework is pages 3 and 4, but you can cross off that whole chart on the top. We're not gonna do it now, and if you notice, the next page, page 5, has a very similar chart, so we'll just do it there. Okey doke. So you have 9 multiple choice questions for homework. I highly recommend actually trying them. I will say page 4 looks really intimidating. That graph looks crazy, looks messy. I promise you, you can do it. Okay, read it, try it, just check it out. It's not so bad. Don't let it intimidate you. All right, the end.